Okay, we're in section 4.4, exponential and log equations. So the first thing that we're going to talk about here is what I hope is something that just would logically make sense. If I have two exponential equations, so if I have an exponential equation that says b to the n power, and I make that equal to another exponential equation, which might be b to the m power. If I set those two things equal to each other, because the bases are the same, in order for this expression to be true, that means that this has to be the same as that. So in this case, since the two bases are equal, I have two exponential equations set equal to each other. N has to equal m. And if that's the case, we're going to be able to solve a couple of basic equations. So let's go ahead and take a look at a couple examples of what I mean by this. So if we have something like 2 to the 3x minus 8, and that equals 16. Well, we can actually solve this equation for x. Notice that the x is in the exponent, so this is an exponential equation. The problem is, right now the two bases are not the same. But you have to recognize 16 as a power of 2. We could rewrite 16 as 2 to the 4th power, because that's what 16 is. So we're going to rewrite the 16, keep the left side the same here. We're going to rewrite 16 as 2 to the 4th power. Now what you should see is that the bases here are the same. Okay, I've got 2 on either side as my base, which means that my exponents, 3x minus 8 and 4, have to be the same in order for this to be a true statement. So we're going to take those two exponents, 3x minus 8, and set them equal to each other, so it'll equal 4. Then we can solve this equation just like we would normally solve any other equation. So we'll add 8 to both sides, giving us 3x equals 12, and then we'll divide both sides by 3, so we'll get that x equals 4. And that would be the solution to the original equation. You can certainly go ahead and plug 4 back into the original equation to give it a check. If you plug 4 back into the original equation, you would get 3 times 4, which is 12, minus 8, which is 4. So you would get 2 to the 4th power, and 2 to the 4th power is 16. So it does work. Okay, let's try one more example. So now let's say that we have 27 raised to the x plus 3. And that's going to be equal to 9 to the x minus 1. Now again, you might be looking at those thinking, okay, well I definitely have exponential equations, but the bases are not the same. And you're correct, the bases are not the same here. But, and this is where it becomes really important that you start to recognize powers of these different numbers. 27 and 9 are both powers of 3. 9 is 3 squared, 27 is 3 cubed. So we're going to go ahead and rewrite those as powers of 3 so that now I'll have the same base on both sides. So this is going to be 3 cubed, that's what 27 is, but don't forget you still have to raise that to the x plus 3 power. And then on the right side, 9 is 3 squared, and don't forget you still have to raise that to the x minus 1 power. Now what I have is I have two things on either side with the same base. I do have to take care of the fact that I have a power raised to a power. And if you remember from the previous lessons, when we have a power raised to a power, we multiply the powers together. So on the left side here, we get 3, and then I have to raise the cube raised to the x plus 3. So I'm going to multiply those two things together, and we're going to get 3x plus 9 as my power. And then on the right side, same idea. The base is 3, but I have to take and I have to raise the 2 to the x minus 1 power, which means we multiply them together. So we're going to get 2x minus 2. Now the bases are the same. Because the bases are the same, the exponents must be the same, which means I can take the two exponents and set those two things equal to each other. So 3x plus 9 equals 2x minus 2. One thing I want to caution you on, we are not canceling out the bases. That's not what happens. Please do not cross out the bases and think that that's what you're doing. You're setting the exponents equal to each other because in order to make the statement true, that has to be true. So that's why we're able to do that and solve it. We are not crossing off the bases. So don't do that. That's mathematically not correct. Okay, so let's go ahead and solve this. In order to solve this, I'm going to get all the x's to one side, so I'm going to subtract 2x on both sides here, and we're just going to get that x plus 9 equals negative 2. And then to solve for x, I'm going to subtract the 9 on both sides, so we get that x equals negative 11. And again, you can go ahead and plug those back in and check to make sure that negative 11 is the solution. And when you plug it back in, it is the solution. It's a little bit more difficult to do there because we're going to end up with negative exponents. But that is how you solve those particular equations. Okay, so now let's say that we have something that looks like this example. 4 to the x power equals 15. Well, 4 to the x is definitely exponential, but I look at the right side and I think 15, okay, so can I make 15 a power of 4? 15 is not an easy power of 4. 4 to the first power is 1. 4 to the second power is 16. That's already past 15. So it's going to be something in between 1 and 2, but it's not going to be an easier one to figure out. So the way we can actually do this is because I have the exponential on the left and I have something which is not an exponential on the right-hand side. I can change this into a log, and what you want to recognize here is that the variable, once again, is in the exponent. This is an exponential equation. When the variable is in the exponent and you have something that looks like this, where I don't have a way to create common bases on both sides, I'm going to have to change this into a log. So we're just simply going to change it like we were doing before into a log. Remember, so this is going to be the log. The base of the log is going to be the same thing as the base of the exponential equation. The base is 4, so it's going to be a base 4. Okay, the log itself is equal to the exponent, so x goes over here, and I am taking the log of 15 because 15 is the argument. And there you have it. I've actually solved for this particular equation. I've actually found the value of x. The value of x here is the log of 15 base 4. Now, that is what is called the exact value, and that's going to be important. This is exact. And I know a lot of us are not used to seeing something like that, when you're used to seeing some kind of an actual number there that, well, this is a number, but something that looks more familiar to you. Remember, this just represents an exponent, and it is an exact value. Okay. Once I plug this into a calculator and it starts to spit out a decimal, that's what's called an approximation. Now, we are going to be able to do that. Again, if you have the calculator that can do the log with a base of 4, then you can just plug that straight in. If not, most calculators can do regular logs or common logs, so we would have to use the change of base formula. So this would be the log of 15 divided by the log of 4. Or you could do the ln of 15 divided by the ln of 4. Either way, it's the same thing. And that's going to give us an approximated decimal when I put this thing into the calculator. And the approximated decimal to this thing is about, I think it's 1.95. 1.95, and you can double check that. Go ahead and plug that in there, but I'm pretty sure it's about 1.95. And that makes sense because, once again, that is in between 1 and 2, and it should be very close to 2 because 4 squared is 16, so that's very close to 4 squared. So this is what's called the approximation. So once you give the decimal from these things, it's the approximation. The log itself, when you just leave it in log form, is an exact answer, and you will be asked to be able to provide both of those solutions. Okay, let's look at one more. We'll call this one up here A. Let's look at B. So let's do 10 to the x power equals 120,000. Okay, this is a little bit bigger numbers. I can tell you that 120,000 is not a power of 10. So we're not going to be able to reduce this that way. So what we can do is we can rewrite it as a log. So we'll say log base 10, because that's the base. it equals the exponent, which is x, but we're going to take the log of 120,000, and that equals x. Again, that right there is exact. And then once again, if you were to plug that into your calculator and get some kind of a decimal approximation, which I did not do in this case, I think it's somewhere in the neighborhood of the 5s. Here, I'm going to actually pause this for a second and then come back. Okay, yeah. So if we were to go ahead and write this, now I did not have to write the base of 10, by the way, on this thing. I just did to make it easier. If we were to rewrite this, it would be the log of 120,000 divided by the log of 10. Now, did I have to really do that? No, I didn't, because the 10 already is in a common log. So I literally just could have typed in log of 120,000 into a calculator, and we're going to get the approximated decimal, which is 5.08. And that is your approximation. Okay, so now we're going to do one which is a slightly more involved example. It's still an exponential equation because, as you can see, the variable is in the exponent. It's in the exponent of the e part, though. In order to solve this exponential equation, the first thing you need to do is you need to isolate the term with the exponential part in it. So we need to isolate this. This right here, this e to the 0.6x, we have to isolate that. We got to get it all by itself. Okay, make sure you understand the 40 is not a part of that. I mean, it's multiplied by it, but it's something we have to get rid of as well. So basically, we have to solve this equation for e to the 0.6x before we can actually solve the equation for x. So the idea is what we need to do is we need to add 3 to both sides. We're going to solve it just like that e to the 0.6x was just a variable like y or something. We'll add 3 to both sides. So we would get 40 e to the 0.6x. Adding the 3, we get 240 on the right. Okay, the exponential equation, the e to the 0.6x, is still not isolated yet. I now have to divide both sides by 40. So when I divide both sides by 40, now we get e to the 0.6x on the left, and then 240 divided by 40 is 6. So we get e to the 0.6x equals 6. The e part now is isolated. The exponential term is isolated on the left. Now I can try and solve this like we were doing before. Well, the idea is what I want to do now is, because I cannot make 6 as a base of e, I cannot rewrite 6 as a base of e, so I'm going to have to use logs in order, or rewrite this as logs in order to solve the equation. Well, notice that the base here is e. So instead of writing log base e, which is okay to do, by the way, but instead of writing log base e, I'm just going to write natural log, because all natural logs have a base of e. So when I rewrite this, I'm just going to write natural log. I know that it has a base of e, and for this one I'm going to actually write it, even though we don't really have to. I am taking the natural log of the answer over here, which is 6. That's the argument. And then the log itself has to equal the exponent, which is 0.6x. Okay, so now in order to solve for x, I literally have one step left. I have to divide both sides by 0.6. So in order to get x, I'm going to take the natural log of 6. I'm going to stop writing the e there and divide it by 0.6. That is your exact answer. Okay, this is the exact answer for x. But now let's say we wanted the decimal approximation. Well, if that's what you want, then you just plug this into your calculator. And when you plug it in, especially if you have slightly different calculators, make sure when you do the natural log of 6, you end the parentheses after you do the 6 here. So I would type it in. Make sure that you put a parentheses around 6 and end your parentheses before you divide by 0.6. If you don't, you're going to get the wrong answer. So the approximated decimal here for this thing is about 2.99 when you plug that into your calculator. And go ahead and give that a shot just to make sure that you get that correct answer out of that.